for organizing everything. It was great.
Okay.
Thanks for staying for the last talk. So yeah, so I want to talk about sort of geometric result, which is through the sort of using the right theory probabilistically, always a cool thing to do. So setting I want to start with is that will get more general in a bit, but like you have a Lie group and you have a maximal convex subgroup. So this quotient G1 K, it's a symmetric space and it's with like a suitable metric. It's a simply connected non-positively curved manifold, but to be non-positively curved manifold in which this Lie group G acts by symmetric. So it's going to be with E is equal to R and X is the hyperbolic plane. So everyone likes that. And then you want to further quotient out this thing by a discrete group. And you get some manifold now, which is not strictly connected, but it's still a positively curved manifold. And you want to sort of there's some various like philosophical notions about what it means for it to be large. For example, you can say that it's small if it's compact. Compact is be small. You can say that you can ask whether it has infinite volume. And there's a remaining volume there. Another thing you can ask is if it has unbounded injectivity. So what I mean by that, like, are there points in M with arbitrarily large injectivity radius? So what is the injectivity radius at a point? It's sort of the largest radius of a ball which you can embed injectively. Or equivalently, if you look like at a point in the pre-image, it's like the minimal amount that an asymmetry in your group like translates a point in this pre-image, whether it's data. Okay, so if you have locally symmetric space quotient with unbounded injectivity radius, then certainly you have infinite volume because you can embed really big balls, so you have infinite volume. The converse is not true. For example, you can have this like sort of cylinder, infinite cylinder, in R3, for example, and it has bounded injectivity radius because the cylinder is sort of finite height, but it certainly has infinite volume because it's infinitely long. Okay, so we want to study sort of what it means for this manifold to have unbounded injectivity radius, for some criteria for it, and for higher rank symmetric space, like this symmetric space of as the length parameters. Fraczyk-Gelander prove a remarkable sort of rigidity here that if you have a locally symmetric space, this is like, so locally symmetric space is of infinite volume. Then it automatically has bounded injectivity radius. So this cannot be higher rank locally symmetric space to get this kind of cylinder. So for rank 1, so it's very nice result published in the X. It's false if G is a rank 1 Lie group, like for example, this PSO2R. Why is it false? Well, you could do this sort of as an exercise. If you have a co-compact lattice in H2, so let's right here you have like H2. Yeah, co-compact. And you have a normal subgroup of that. So for example, you can have quotient with Z, then H2 mod n will also have finite injectivity radius. For example, if gamma mod n is Z, you have this sort of one-sided infinite surface, so it's like the Z cover, it's sort of like the cylinder thing, but it's like a quality. So this is called injectivity radius. So why can you do this in rank 1 but not in hyperbolic? Well, because co-compact lattices in rank 1 groups, they're hyperbolic. They're hyperbolic groups because rank 1 symmetric spaces are grown of hyperbolic spaces. They're negatively curved. So hyperbolic groups have infinite index, infinite normal subgroups. But lattices in higher rank Lie groups don't have such subgroups by Margulis normal subgroups either. Yeah, so you can do this in rank 1 and not in higher rank. Following some questions of this and more precise questions of Fraczyk-Gelander, Arie Levit and I wanted to find some sort of optimal version of this theorem of Fraczyk-Gelander that works in rank 1. So maybe some quantitative criteria and decides whatever that means of this discrete group proportioning by for M to have unbounded injectivity radius. And we found it in terms of critical exponents for exponential growth rate of the group. So we showed that if gamma has a small critical exponent, then this M x mod gamma has unbounded injectivity radius. So what is critical exponent? So if you went to somewhere else, like for example, you know what it is. So if you have an action with an asymmetric space, you can define this critical exponent as the exponential growth rate of number of orbit points in the ball. So you take some big ball, you look at how many orbit points are in it. Hopefully your action is probably discontinuous, so this is finite. But like it gets bigger and bigger when your ball gets bigger. And so then you take the log and divide by r and hope that you can produce something. I mean, if you all, so in this case, hyperbolic setting, we're talking about you will convert to something, otherwise, okay, I didn't here this only convert to something. But so one of the sort of magical things about the critical exponent in the setting of isometric groups of normal hyperbolic spaces is that like any discrete and compact isometric groups of a normal hyperbolic space has the same critical exponent. So it's some invariant of the space. We can call it, for this reason, just delta x. You can interpret it as the Hausdorff dimension of the Gromov boundary of this space with respect to a certain visual metric, but that's not going to be particularly important in this talk. And this delta x, so it's the largest possible critical exponent of a properly discontinuous subgroup of isometric of x, which makes sense because, like, the biggest discrete subgroups you could have are the ones that are compact. You make them any bigger, they'll stop being discrete. Okay, and in sort of concrete situations, if G is PSO R and X is the hyperbolic plane, then the critical exponent of a lattice is 1. If you're working in the isometric groups of Hn, this critical exponent is n minus 1, and there's formulas for other rank 1 symmetric spaces. Yeah, find them on the internet. Okay, so what did we actually prove about critical exponents of injectivity of when small critical exponent implies about injectivity radius? So in the setting of rank 1 symmetric spaces, if you don't know what it is, you can always keep in mind H2 is not simpler in the general situation. So yes, you have a rank 1 symmetric space, and you have a subgroup of the associated Lie group, which acts by symmetry. So if your discrete group has smaller critical exponent, or at least as small as half the maximum, then the quotient has unbounded injectivity radius. And we have an analogous theorem in this more general setting of hyperbolic spaces, with some caveats that we have to assume. So two sort of weaker things in this more general theorem of more general hyperbolic spaces. One is that you have to assume that your sort of smaller subgroup is contained in a lattice, which you don't for symmetric spaces because for some technical reasons. And the other thing is we have to assume that the critical exponent of gamma is actually strictly less than half the maximum rather than less or equal than half the maximum. This assumption can probably be removed. So in particular, this applies to the second theorem applies to a hyperbolic acting and its scaling out. Okay, so this first theorem, so this says that if you have critical exponent less than half the maximum, that you have about injectivity radius. So you can say, is there a way to strengthen it? Maybe if you have a critical exponent of like less than like 2/3 of the maximum, you also have an unbounded injectivity radius. So this is not the truth. So this is related to a problem I stated in the problem section. So if you have a co-compact lattice acting on H2, then Taylor and Mrs. and Taylor constructed a sequence of normal subgroups of this lattice, whose critical exponents converge to half the maximum. And like we said a few slides ago, portions by these normal subgroups have to have bounded injectivity radius. Not uniformly bounded, they're going to, as n goes to infinity, there's maximal injectivity radius will converge to infinity, but like for each individual x mod and mod f and sub n will have bounded injectivity radius. And I asked in the problem section, are there such examples in the Asymptotic groups of Hn, in hyperbolic groups with form metrics for general hyperbolic spaces? Some people in the argument said they have some ideas about that. I'm not gonna name. Okay, but so yeah, so that's a nice theorem. So to prove this theorem, I don't actually know anything about hyperbolic manifolds. So if I was able to do it,
this meeting is being recorded.
Thank you. So if I was able to do it, it probably involves something some ergodic theory. And specifically, we use the notion of stationary random subgroup. So what's okay, this is like not much, but there's a way to interpret critical exponents in terms of the smallest eigenvalue of the Laplacian timing operator. So if you quotient are of a locally, if you have a locally symmetric space, then like it's less than the critical exponent is less than half the maximum. You can only give the quotient manifold as the same eigenvalue of the Laplacian operator as the whole group, like as the universal power. So in other words, to state our theorem about critical exponent is that like if you have a locally symmetric space whose binomials like Laplacian spectrum is the same as that of its universal cover, then it has a boundary utility radius. So this is actually the forum in which Fraczyk-Gelander asked this question. Okay, so to prove all these theorems, we use some probabilistic notion called stationary random subgroups. So what are the random subgroups? So suppose you have basically any group, and you consider the space of all closed subgroups of the group. So you can look at like the Hausdorff distance on this space. This is called the Chomsky topology. This is very nice. It's even metrizable. There's some gaps, but it's very big, but that's okay. The group G acts on this on the space of the closed subgroups continuously by conjugation, and a stationary random subgroup, so we call it asserts, is a stationary measure, stationary probability measure on the space of subgroups of G. So what does stationary mean? It means if you sort of average it with respect to one step of your random walk, like the average with respect to you get it back. So very special case of stationary measures, which are stationary with respect to any random walk, are the invariant measures. So if nu is invariant under the conjugation action, then you call it an invariant random subgroup or IRS. And IRS, so this is a subject that has been studied sort of for a long time now. It generalizes the notion of lattices and normal subgroups. You can use IRS as the SL2R to sort of contact it by isolate space in an interesting way. You can do lots of things with it. But like sometimes it's not enough to consider invariant measures. You also need to think about stationary measures. So that's what we did. Okay, so the key sort of organic theoretic probabilistic tool is that we needed to estimate, prove this theorem that small critical exponent implies an boundary injectivity radius is an estimate on critical exponents of stationary random subgroups of hyperbolic detecting hyperbolic spaces. So in the most general setting, so we started working on this for invariant random subgroups instead of stationary random subgroups, because I didn't know what a stationary random subgroup was about 5 years ago. Both was the BTL, and at the time we didn't have this eventual application in mind, but it was just like something cool to do. So 4 or 5 years ago, we showed that invariant random subgroups of this of a group of asymmetries of a chronal hyperbolic space, which is large enough to contain co-compact lattice, is either like super small or quite large. So suppose you have say an IRS of G. Then so IRS is the measure, so you can check about like for almost every subgroup with respect to this measure. Either it's super small, so it's contained in the amenable radical. The amenable radical is the maximal group that acts trivially on the global boundary. So for symmetric cases, the amenable radical is just the identity. Well, even if X is a Gekhtman is one space, the amenable radical is just the identity. For hyperbolic groups, it's like something like. So in any case, it's something that's super small. Or this group is quite large, in the sense that its critical exponent is more than half of the maximum. So that's for invariant random subgroups. Okay, for stationary random subgroups, stationary means you're stationary with respect to some measure, so some random walk. So we wanted a similar bound, but of course, this bound would have to depend on the random walks amount. So, so now you assume something nice about this measure. So we assume that it's actually supported on some co-compact lattice in G, and has nice moment condition. So we show that any US recipe. So again, either it's essentially the identity, like it's supported in the amenable radical, or its critical exponent is strictly bigger than the best entropy H of U of the random walks, divided by twice the drift of the random walk on this case. So I'll say this more. So if you went to Charles stock, or Sharp or Richard Sharp stock, what these things mean. But I'll just mention for now that in general, this quantity H over L is less than or equal to this critical exponent. But when your space is metric state, then you can create a field, like certain discretization of Brownian motion, so that this is equal to delta x. So this particular random walk, the bound that we get for SRS is the same as for IRS. And this is important in our theory. So
Can I ask?
Yeah.
So are you saying for almost every subgroup that like it can both happen that it's in the amenable radical or this other thing?
Yes. You can choose a subgroup. The measures are funny things, right? So you can choose like measure to have 2 points. One is like something in the amenable radical, and one like one is the identity, and one is the.
Okay.
But of course, if you assume that your measures are varying or something, then it's one or the other. So just brief sort of remark, like what is entropy and drift? This makes sense for like any random walk. So the entropy is sort of intrinsic measure of like how fast the convolutions of these random walks grow, and this depends sort of only on the measure. This has nothing to do with the action. The drift is like how much on average you get farther from the base point in one step. So u star n is like after n steps of the random walk, and then you divide by n. And there's this magical inequality of March and dependency airship that links these three estimates. So entropy, which depends only on the random walk, drift, which depends on both random walk and the action, and the critical exponent, which depends only on the action. So they're less than, if you have this inequality, and when there's an equality, it means your random walk is very special, so it's very suited to the geometry of the loop. But if you have a symmetric space, and you choose U to be discrete for Brownian motion, then I made a typo here. They should say H of U should be equal to Lx of U and delta x. They should be in the second bullet point, they should be inequality. So you can choose it to be equal, then if you have a Taylor graph with a hyperbolic group, then I'm not sure you can choose it to be equal, but you can choose it to be arbitrarily close to the first one. Okay, so I stated the theorem for SRS. I stated the theorem for injectivity radius. What do they have in common? What do injectivity radius have to do with stationary random samples? Okay, so first, suppose you have giving it symmetric space anyhow. Suppose you have symmetric space and fix a point P, in the symmetric space. So by sort of how multiplication works, or I guess because G has by symmetry, the injectivity, so if G is any point in your loop, any element in the loop, the injectivity radius of x mod gamma at sort of the foot point of GP is the injectivity radius of x mod the conjugate of gamma at the point P. Okay, so now we're considering discrete subgroup H. And we assume this critical exponent of H is pretty small, so it's at most half of the maximum. So we want to show that x mod H has a boundary injectivity radius here. It has points with arbitrarily large injectivity radius. And with this remark, in the second point, it's enough to find, instead of like fixing your manifold and changing the base point to find the big injectivity radius, it's enough to fix the base point and sort of conjugate your group to find one that gives you big injectivity radius like at the fixed base point. Okay, so first, so how do you get measures involved in this? So first, nice sort of exercise in the geometry topology. If you have a sequence of subgroups of your group G, Hn, they converge to the identity subgroup. So identity, a united element with like the subgroup, which the trivial subgroup. Then you converge to the identity subgroup. If and only if the injectivity radius at x mod, at the base point of this thing converges to infinity. This is intuitive because if you just like put in Hn equal to infinity, then of course it has injectivity radius infinity everywhere. And this is like, be nice. And if you now, so now instead, we look at measures on sub G. And the space of measures on sub G, they come with their own topology, so they come with the weak star topology. And a sequence of measures on sub G, which shows that they converge to the Dirac measure on sub G. So this is the measure which gives it's the probability measure that gives full weight to the identity subgroup and nothing to everything else. If and only if, like, it gives, if and only if, like, you plug in everything with like injectivity radius, and the measure assigned to it by UN converges to 0. So yeah, you have this AR, the set of K subgroups with injectivity radius at the base point of the one R, and the UN of AR converges to 0. Okay, so now we're ready to like talk about measures. So suppose you fix a nice measure, nicer than Pocket. So this is discretization of Brownian motion to uniform lines. So it's a measure with moment conditions, and it satisfies this critical exponent times the drift equal to entropy. So in particular, we can use the SRF theorem, this with what happened. And we want to somehow use this measure to prove something about the injectivity radius of x mod h. Okay, so you have this measure, you have a subgroup with small critical exponent, and you consider a family of measures on sub G. So what do? You look at the Dirac measure on H. So it's the measure on the space of subgroups, which gives, which has an atom and H and 0 to everything else. And you convolve it by n steps of the random walk, which is sort of, you look at like where, like you basically conjugate it, you take n steps of the random walk, and then you look at like all the conjugates of H by those elements. So by definition, you get this thing, in the second line. So it's the I is like you look at everything after I steps of the random walk, and yeah, you conjugate by you group by it and look at the probability that it's in your like fixed set. And for technical reasons, you don't just want to look at the convolutions, you want to look at cheddar rather than the convolutions. And so take n convolutions and then divide by n. So why would I want to do this extra step with cheddar averages? It's because if you take like in any sort of for any group action, for any measure in the group, if you take a Wigster limit of these cheddar averages of convolutions, convolved with any measure, any measure you want to start with, then you get something stationary. So it's somehow, if you don't, in math a lot of times, like if you don't really, it's easy to write. It's sometimes very hard for constructing variant measures. A lot of times they don't exist, but it's sort of easy to construct stationary. Just after kind of sense. So okay, so a certainty of these measures is stationary. What else do you know about these Wigster limit? Well, each this UN is supported on conjugates of the subgroup H you started with. So, and the critical exponent is the variant conjugation. So it's supported on subgroups with critical exponent less than half the maximum. And now you do some stuff. So you want to show that in the limit, you still supported on subgroups with critical exponent less than half the maximum. And this turns out to be true because there's several steps in this. First, you have to show that it's like supported on discrete subgroups, which is like something hard or more so. But it's proved by Gelander, Levit, and Margulis, using Margulis's brain. And the other step is that in the category of undiscrete, when restricted to discrete subgroups, the critical exponent is upper semi-continuous. So in the limit, the critical exponent, like, it can get smaller, but it can't get any bigger. It can get smaller, for example, you start with a uniform lattice, and then you take like lots of finite covers, then you convert to the identity. Okay, so the limit is 0. But if it gets smaller, then it can't get any bigger. So this limit measure also gives the way to subgroups with small critical exponent. Okay, so this limit is an SRI supported on things with small critical exponent. But because of this SRS theorem, so this 2023 thing, if you have an SRS which is supported in things with small critical exponent, well, then almost really it has to be the immutable radical. In this case, we're in the symmetric space that means the immutable radical is just the identity. So it means that these measures mu n, they actually, so it means mu is the Dirac the identity, because that's the only thing it could be. It means that you have a measure which is full way to the identity, so it's Dirac to the identity. And this is true like for any unit of a subsequence. So it means mu n converges to Dirac at the identity. Dirac measure the identity. So how do you so how do you unpack that? From the definition of this measure, it means the weight that mu n assigns to this that A of R, like to the subgroups, the portions by which have bounded injectivity radius less than R at the base point converges to 0. So you look at all the points G in the group such that the injectivity radius at GP of x but h is less than R. It's the same as like the Cheddar average of the measure assigned by mu I to the elements of G, such that the injectivity radius of x minus the conjugate of G at the base point is less than R. And this is the same thing as mu n of AR. And this has to converge to 0. Okay, so the only way this could be true is if for any individual R, I mean, there's lots of points with injectivity radius greater than R. So it's like, you can't find like any specific point, but you show that this is true for essentially almost every point. And okay, so this is how you prove this theorem. And the proof that of the stationary, the proof of the stationary theorem about critical exponents and so stationary random subgroup, it revolves, it sort of goes very deep into random walks and groups. Okay, so I don't have time to talk about it, but it's cool. It uses like Pakistani theorem. Okay, I'll finish up.